because given what David was saying about ion traps, also something that Martin was saying about simulation, I thought I'd swap them over. So there's a sort of menu of things that I was going to cover in this lecture. Okay, so there's the menu. I'm going to talk about a little bit of history. And there's bits in there just to keep you awake. In particular, why washing makes you heavier. I'll explain what that means towards the end. So what I'm going to do is talk about some stuff that depends on coherence, and in particular on atomic coherence, especially trapping kind of things at the beginning. I'm going to explain why, almost certainly in terms of quantum technology, that will be the biggest impact that our field could make in terms of real technologies. Then I'm going to do a little bit about secure comms, just to introduce the idea. Then I'm going to talk a bit more about metrology, especially about quantum limits on metrology. And some stuff about Casimir if I have time. So that's the sort of menu for now. Okay, so in terms of a roadmap of difficulty, I borrowed this. That's less good, isn't it? Was it there initially, or was it just me?
It was. It just flashed off.
Projector's off. Does anybody know how to? I can turn it around and make a little square, a little squint with my laptop. Aha. Projector. It's flashing off. That's good, isn't it? That is actually, isn't it? There's no light.
There is a red flashing light.
Hmm?
There is a red flashing light.
Can we get on the call?
Press that one. Right, okay. I borrowed this from this roadmap from Tim Spiller and Bill Monroe in terms of difficulty, some unquantifiable units versus number of qubits, about things that are straightforward, things that might be possible, things that look really hard. And by the time you get to quantum computers, you're up at millions of qubits, and it's really going to be really hard. Quantum key distribution, which I should mention towards, I don't like the way it flashes. Don't mind. Quantum key distribution down here, it's essentially marketable now. Quantum metrology is becoming useful now, as we'll hear from a number of people. Simulators, something that Martin just talked about. Quantum repeaters, a bit more difficult, and then quantum computers, incredibly difficult. Okay, so what I'm going to focus on, therefore, is what's down there that you might be able to do within a reasonable scientific lifetime. Right, now quantum-enabled technologies. I think it's really quite important to realise that we're actually living in a quantum-enabled world already. And in particular, you know, the first quantum revolution exploited the fact that there were stationary energy states, energy levels, and you had transitions between them. In doing so, you know, it led to transistors, lasers, and so on. Broadband internet is only really possible because of erbium-doped fibre amplifiers. Erbium-doped fibre amplifiers are essentially short-noise limited. They're quantum-limited amplifiers. There's an erbium-doped fibre amplifier over there. And the only reason that you can get the sort of bandwidths that we actually got used to in terms of telecoms is because it's actually quantum-limited. And I would claim that this has made the greatest change in the world economy that we've seen since the Industrial Revolution. I mean, it's something that you underestimate, really, but certainly quantum optics applied to that amplifier that was embedded within optical comm systems has actually enabled the whole of the e-commerce revolution. A second quantum physics revolution exploits coherence, atomic clocks, GPS, sat-nav, magnetic resonance imaging, secure comms, and if I have time, I'll come back to this thing that I know that Martin's going to talk about a lot tomorrow in terms of how nature exploits these things. Oh, and I'll explain what these geezers in suits are later on. Okay, so look, we've been networked, as it were, for a very long time. Now, this is a 100-year-old map showing how the telegraph system enabled the world to be networked. So you see that there are all these cables going across the Atlantic, through the Mediterranean, down the Red Sea, round through to India, connecting up then to the rest of Asia, and going the other direction, of course, across as well. And curiously, if you look at where the high bandwidth, the 10 gig pipes are for optical communications, they're pretty much laid in the same way. Okay, so we've been networked for a very long time. Now let's start thinking about atomic clocks, because that was mentioned several times. David mentioned about how really good atomic clocks are necessary for example, the ion trap stuff that he was talking about. So this is Rabi. Rabi started in the 1930s pioneering atomic beam experiments, and in particular, if you use atomic beams, you've got no Doppler width. You state selection of Stern-Gerlach magnets, you could do both selection and analysis. The reason that these things are often called flops is because you have a Stern-Gerlach magnet that focuses the atoms out, and a following Stern-Gerlach magnet in the next part of the region to flop them back in again. Okay, so that's the reason why they're called flops. And Rabi got the Nobel Prize for exactly this kind of ultra-precision experimental atomic physics. Okay, I love that cartoon. Right, we'll get rid of that now. Okay, so Ramsey. I mentioned Ramsey earlier. There's Norman Ramsey. Anybody other than me ever met Norman Ramsey? Apart from Ed Whitten, he's got the largest distance between eyebrows and the top of his head of anybody I've ever met, which is deeply scary. Okay, there's Norman. And what he proposed is that whereas what Rabi talked about was a single magnetic resonance region which flipped the atoms over, so you have a Stern-Gerlach magnet as a state preparer, a Stern-Gerlach magnet as a state analyzer, detector, a constant magnetic field region where you do the RF transition. What Ramsey said is you can't really make that RF region longer and longer and longer because you can't get the magnetic field homogeneous over those huge distances and get the RF frequency amplitude stabilized appropriately. But if on the other hand you had a separated RF region, one there and one there, in other words a cavity and a cavity separated by a distance, you get quantum interferences between the amplitude of driving it in the first cavity and the second, and those quantum interferences give you very narrow lines. So suddenly atomic beam machines got very, very long. Ed Hind's PhD thesis, DPhil thesis in Oxford was the longest beam machine I've ever seen, and they had to knock a hole in the wall to put the detector in the bike sheds. Okay, it was an enormously long machine because the longer the distances between the RF regions, the narrower the resonances are, just by Fourier. Okay, so incredibly long machines. Okay, so what happened then is, given that you've got this selectivity that Rabi pioneered, and the separated fields to get these very sharp interference lines, it became obvious to people that were knowledgeable about this that you could build atomic frequency standards. Okay, the first person to think about this was Ken Smith. Ken was then at the Cavendish. He became the founding experimentalist at Sussex, and Ken had worked with Ramsey, and what he did is he persuaded the people at the National Physical Laboratory in Teddington in England that this could form the basis of the first atomic clock. So the people involved were Essen and Parry. Essen and Parry. And you can see that in those days, apparently, you needed to wear a suit to work in the lab. And that's the first atomic clock. That's NPL1, and it became the standard for what eventually became the redefinition of the second in terms of atomic standards. The problem is that the beam machines got longer and longer and longer to get narrower and narrower lines. But people thought, well, actually, if I had slower atoms, it would do the same thing. Okay? So if I could have slower atoms, you could do that. Now, what Zacharias at MIT suggested is that what you could do is build an atomic fountain. You could use the stairwell at MIT and fire atoms up the stairwell in a beam machine. And gravity would mean that, eventually they fall down again. So what you should do is take the really slow atoms right at the top of the atomic fountain. So he built this bloody great atomic beam machine at MIT to do just that. The problem is that the proportion of the atoms that get right to the top is essentially zilch. So the signal isn't there. Okay? So although they built the machine, it didn't work. But what you can do instead, and this happened 35 years later, is you can make, with a magneto-optical trap, a whole bunch of cold atoms, and then just throw them up collectively into a cavity and bring them back down again. So that's an MOT, a magneto-optical trap fountain, and the new atomic clocks are exactly of that kind. Okay, so the fundamental unit, the fundamental definition of the second uses clocks that use exactly that. Okay. Right, so here's various sorts of clocks. Okay, there's the primary standard, which is the cesium beam standard. It's got a fractional accuracy of 10 to the minus 15 years. It loses a second every 100 million years. It's quite bulky, consumes a kilowatt of power. That's mainly in the vacuum systems. It costs about $1 million. Okay. Then a commercial beam clock, that's a secondary standard, which in the old days Hewlett-Packard would have sold you. Costs about 50k. It's got a fractional accuracy of 5 to 10 to the 13. The compact ones, little cells, rubidium cells for example, fractional accuracy again down by 3 orders of magnitude. It loses a second in 1,000 years. It consumes a watt of power, and you could buy one of those things for $1,000. Okay, quartz crystals do that, and your wristwatch does that. I think it's unbelievable that you could put a wristwatch like this, but still, there you go. So there's size-power ratios. Right, so let's look at other ways that you might want to build a clock. And I'll come back to why you might need clocks in a bit. Okay, so I need to introduce the idea of coherent population trapping. And there's a really funny history. Coherent population trapping is the establishment of dress states that don't couple to the external field. So you can't, they're basically immune to photoexcitation. Linear combinations of atomic states where the dipole moments cancel. The curious history to this is that they were observed first in Pisa. No, I'll start again. They were first published from the observation in Pisa by Gozzini, Alzetta, Arimondo, Orioles, and Moy. So basically, and this is Ennio Arimondo, who's still active and doing lots of stuff. Orioles was the theorist involved. And what they were doing was an optical pumping experiment using a multi-mode dye laser. And what they were doing is putting a field gradient in their optical pumping cell so that resonance frequencies occurred at different spatial places. So you see a bright line here and another bright line here for the various resonance frequencies, spatially separated by the gradient of the magnetic field. But what they saw in the center of their cell was a dark line. And the dark line indicated that the atoms had turned off in some funny way. Okay. And then Ennio Arimondo and Orioles then worked out a raft of theory for these things, and they published it. So that's the first published account. It turned out that their multi-mode laser, some of the neighbouring modes in the laser were phase locked. That's going to be important for reasons I'll explain in a moment. Carlos Stroud in Rochester, with his group, went out looking for these uncoupled dress states because they'd seen from first principles there should be such things. Okay? So Carlos Stroud, within a few months of this experiment being published their own, which they'd gone out to look for deliberately, looking for uncoupled dress states. But two separate groups had already seen this, but were prevented from publication by classification processes. Bruce Shaw, famously in Livermore, and ourselves working at Harwell. And what this was to separate isotopes. And you can work out what sort of isotopes because of the word Harwell and Livermore. Okay? And it was classified. And let me explain what actually we were trying to do. What you would like to do is use resonant photoexcitation to extract one particular isotope and not another. Okay, so you have a ground state, an excited state, and then you could ionize them and collect them. Okay, and the other isotope would be not resonant, so you don't collect them. Right, so that was the background. And then, of course, the problem is that in any interesting isotope, there'll be more than one ground state because of hyperfine splitting. Okay? So the obvious thing to do is, if these are thermally populated, half the population's in there, half the population, roughly speaking, is in there. Okay? So in photoionization, you've actually lost half your population because you didn't resonantly couple those out. So what you do is you put another field on. So you have a resonant field between 1 and 2, and a separate resonant field between 3 and 2. And when you do the analysis of this stuff, and you turn on both fields, and you grind out the calculation, you only get half the population. I think that's very odd. I put another field on, and it hasn't given me anything at all. And what's happening is that you're generating a superposition of 1 and 3, which is anti-symmetric. The dipole moments cancel, and that anti-symmetric combination of 1 and 3 doesn't couple to the light field. And that's population tramping. Okay? So we saw it, and Bruce Shaw saw it, because we just couldn't get that one out. Okay, there is a way of getting it out if you randomize the phases, by the way. Right, but once we've seen this, we started thinking, well, actually, these things, because they're superpositions of 1 and 3, and they're ground states, these are stable states. And therefore, you should be able to generate incredibly narrow lines. And in fact, these are the dark lines. So you look at the property of excitation, and it dips down and out again. So this is this dark line resonance. And the width of these resonances can be made extraordinarily small. In fact, then what you can do is to have two separated, black, hit it with a pulse, wait, hit it with a pulse, and you get Ramsey fringes again. So Brian Dalton and I played a lot with this because it's interesting that if this is a phase fluctuating laser, if the two lasers are independently phase fluctuating, the coherent population trapping amplitudes go. Okay, they're not stable. If, on the other hand, you've got a common source of phase fluctuations, for example, if those two fields are derived from a common field by modulation, then the field phases are randomly stochastically fluctuating, but are correlated. It's like your windscreen wiper on a completely mad car that's completely stochastically fluctuating, but the difference between them is 0. Okay? And because that's the lambda system, you get an e to the I phi going up, so there's a phase, and e to the minus I phi coming down, it cancels. So you get these very narrow lines, even if you've got a phase noise laser. And that's why the group in Pisa saw a dark line, because different modes of their multi-mode laser were phase correlated. Okay, so a complete accident. Right. Pitch this from Joe Everly. This nice slide, which actually does what I just said. In optical pumping, you've got all your population down there normally. You put a field on, and it fluoresces. But of course, it can fluoresce down to this state as well. That's not coupled. So what you do is you pump everything out of there into there, and it stops. That's optical pumping. Okay, that's what Castellare got his Nobel Prize for, amongst other things. So you think, okay, I know what to do. I'll put another field on to get it out of there and empty it again. Okay, so here's the two fields, solves the Schrodinger equation. You've got dipole moments between here and here, dipole moments between here and here. There's the three-level equations of motion. We're detuning the Rabi frequencies. When you're on two-photon resonance, what you discover is that there's a dark and a bright amplitude. Here's the bright Rabi frequency. The dark Rabi frequency is 0 when the fields are constant. Okay, so it just cancels. And as Joe handwriting says, Arimondo, Orioles understood this. Whitley and Stroud looked for it deliberately, and some of us found it just by numerical handle cranking. Right, nice physics, so what? Okay, well, let's have a look. This is an atomic clock based on coherent population trapping. This is the basic idea of it. We have a local oscillator, okay? And what we're going to do is excite that lambda transition. We'll detune a fair way from resonance there, because we don't really want to get population up and we just want to drive to and fro. And what we'll do is we'll modulate that diode laser at the modulation frequency equal to the transition frequency between 1 and 2. Okay? Modulation puts sidebands out. The sidebands then give you that one and that one. Okay? So as long as you lock it. The big advantage now for an atomic clock is all you need is a modulator for the local oscillator. You don't need an RF cavity. RF cavity is a big, bulky, expensive, and a pain. So if you've got a modulator in there, and if you have the right sort of diode laser, like a VCSEL, it's dead easy to modulate a diode laser. Okay. So modulation goes back to Bell and Bloom about 1 million years ago. Okay. Right. So the person that really pioneered this, Leo Holberg and John Kitchen at NIST, and they found that you could make really small ones. So in fact, you could buy these things commercially. The leading company here is Symmetric. If I'd have shown a slide of clocks 20 years ago, it would all have been Hewlett-Packard. Okay, but now there's Symmetric, Kernco, Stanford Research Systems, and so on, and they will sell you some of these miniaturized clocks. Right. Oh, and sorry, there's something I meant to say there. And of course, they're used a great deal for network synchronization. So in a network world, you need to be able to handshake with synchronization. So a lot of the Cisco router systems, the timing is absolutely locked in by atomic clocks. Okay. Right. So what would be really good to do is to have even smaller ones. And there's a reason for it. We're wholly dependent on GPS for all sorts of things. Your smartphone is GPS, all of your geolocation depends on it. A great deal of trade depends on it. It's extremely easy to jam GPS. Okay, we did an experiment where we managed to spoof the GPS in the English Channel so that shipping in the English Channel thought they were in Winnipeg. Okay, it's dead easy to jam GPS. In fact, it's quite illegal, but in the US you can go and buy GPS jammers now by going to the right sort of store. Well, actually the wrong sort of stores. So we're wholly dependent on GPS. So what you actually need, if GPS goes down, which it's likely to do with the sort of magnets around, is to have a flywheel system. So that in your local communication device, it will flywheel until GPS comes back up again. Okay? So when we build a quantum computer for factoring, you probably will sell 5 of them. If we can build a compact GPS-resistant flywheel that will go into routers and comm systems, you might well sell 1 billion of them. Okay? So when we talk about quantum technology, it's important to recognize where the markets are. Okay? So wireless communication systems, remote sensing, data logging, all sorts of things depend on that. Okay. So let's have a look at John Kitchen's design for this, because John is the leader in this from NIST. Okay? I love calling them kitchen clocks. Everybody thinks I'm saying kitchen. It's kitchen. Okay? As I said, VCSELs, a little cell, modulator, Okay, so there's the modulated wave packet, the little cell with the atoms in, and the cell is about the size of a device. Detector feedback electronics. If you strip it out, what's going on in here is there's your VCSEL semiconductor laser, filters quarter wave plates to get the right orientation for these things. There's a little cell, as I said, it's the size of a grain of rice. Detectors, feedback electronics back into the modulator. Okay? At the moment, you're limited by just one thing alone, which is the heater that keeps the alkali atoms from sticking on the walls of the cell. That's the only thing that limits you at the moment. Okay. So, there we are, it works. Frequency standards. It's got a variance over a second of 3 parts of 10 to the 11 rather. This is based on rubidium 87. Okay. So these basically are commercially available. So these things are basically chip scale atomic clocks. We'd like to be able to miniaturize them even more. We will be able to, you can imagine, dealing with either fibre-based or chip-based systems. And if they're available, there's a whole raft of things, not just the GPS resilient thing that I just mentioned in terms of geo-location, which I think is really important, but it will enable us, if we had these accurate clocks, to do a whole raft of things. And Martin already introduced the idea of quantum limited sensors. These things have the ability to act as accelerometers, gyros, to look at a great deal of squid imaging, for example. It will replace a lot of imaging so you can actually detect magnetic field variation in the brain, and a whole raft of these things. So it's likely that miniature atomic clocks are going to be the first really serious market for quantum technology. Right, information processing in the quantum world is what I should turn to next. It's worth remembering Moore's law. Okay, Moore's law is purely historical. It's got no scientific value to it other than that's what things have done. Transistor elements on the chip get smaller and smaller. Memory doubles every 18 months. Cost diminishes. Now, in the next slide, which you may not be able to see with the lights up, I've got an invoice from the Rutherford lab where they bought a big upgrade to the computer. Okay, this was the National Computing Lab, the Atlas Center. Okay, and the upgrade was to generate a megabyte of memory. Don't laugh. 1974, it cost £400,000. Okay, that would have bought a street of houses in 1974. Can you see it? That's the invoice. Okay, and because £400,000 was a lot of money in 1974, it had to be signed off by the director of the Rutherford lab, Godfrey Stafford. So here's Stafford signing off for this 1 megabyte. Okay, right. Well, if it cost that amount, it meant that in 1974 it would cost 400 million per gigabyte. Now, if you look at Amazon, I think they might have come down even since I grabbed this one. Amazon will sell you this terabyte of store for £45. Okay? Now, if we use the same scaling and not thought about the advances in computation and IT since 1974, in fact, what would have happened is to buy a terabyte would have consumed the entire UK GDP. Okay? So, Moore's law has really saved this. This thing, that's a megabyte. Okay? It's not that long ago for me. So it's before you were all born. It wasn't long ago for me. So here's a picture I grabbed from Scientific American. Okay, it's great that you can quantify brain power. By the way, that's the number of instructions per second against year. And so if you look at some of these things, there's the Apple II, which is the first portable machine I ever bought. Okay. There's the Cray 1 that I did my first supercomputer calculations on. It's quite ironic that right up here is a PlayStation, by the way. Okay, now you compare it with biological organisms where they're processing we're actually already beating the guppy. We're getting close to the mouse, and I'm really terrified about this guy. Okay. Now, will Moore's law actually continue forever? No, it won't. And it won't simply because the number of electrons involved per gate interval is also halving. And eventually, we're locked in. Did you hear that? So you can't get out. Don't unlock that door. We are technically locked in. Right, good. And of course, what will happen is you can't get less than 1 electron per gate interval, so we'll hit a brick wall, and that brick wall is likely to emerge relatively soon. Okay. Right, so let's think about quantum simulation. That's Richard Feynman. Okay? Where did the ideas of quantum computation come from? The first papers that really started to worry about, there's a completely unreadable paper by Benioff from 82. Has anybody ever read it? I was about to ask the next question. Anybody understand it? Have you tried, Martin? No. I can't. I have no idea. But Feynman wrote a fantastic paper in 1984 talking about the power, the fact the inability to simulate, and I'll come back to that in a minute. David Deutsch then showed a whole raft of examples of things you can do. Quantum parallelisms, these guys turned up and worked out the beginnings of the advantages of parallelism. The whole explosion was with Peter Shaw's paper in '94, and as David Lucas said, what happened is that Arthur Eckert turned up at the ICAP conference in '95 and explained about how you get this change in complexity and factoring, and really explained what Shaw was doing to an atomic physics audience. Okay, physical implementations, very quickly. Sirac and Zoller came up with this idea of gates, and loads and loads and loads of people started to work on it. Error correction. Now, in 1994-5, there was a Santa Barbara Institute for Theoretical Physics workshop on computation. Well, there were about 25 of us there, and Serge Roche and I had really come to the view that quantum computation was nonsense, because decoherence was always going to beat you, and the ability to build large-scale arrays of qubits was impossible. So Serge was going to write a Physics Today article with me about how making Schrödinger cats, which is what computation is impossible because of decoherence. And at that meeting in Santa Barbara, Peter Shaw and Andrew Steen explained about error correction, that you could protect qubit superpositions without reading them out, and that meant that you could do fault-tolerant computation. And that transformed everything. So at this point, I thought it was all garbage. At that point, I became a little bit of a convert, saying it was not garbage. And Martin will remember me changing my mind, I think. Right. So let's look at some realizations. Some of this was covered. Well, there's lots of realizations. Ion traps, neutrals, solid state, optical. And you're going to hear bits of all of these things during the week. Okay, but what I'm going to concentrate on is some simulations. Okay. If you've got a reasonable number of qubits, you can start doing non-trivial things for simulations, which are sort of halfway up in this difficulty map of Spiller and Monroe's. Okay. So, for example, let's see if we can simulate the Bose-Hubbard model. So there's the Bose-Hubbard Hamiltonian, okay, where there are basically terms which tell you to hop from one side to the other, and then to say, no, don't sit on my side, I'm already there, okay, and tell them to stay away. Okay, so there's a competition between U and J. That's Hubbard, okay, and the Bose-Hubbard model is actually a really interesting model, which is an idealization of a lot of things that relate to strongly correlated systems, especially high TC superconductors and so on. So can you actually use these in terms of simulations? Right. Well, in quantum optics, you can simulate a vast number of Hamiltonians. You can make emission couplings by choosing the right detunings, for example, either with trapped ions or with cavity QED. And a lot of theorists did a lot of work on playing with this, and a lot of experiments were done. In open systems, you can also engineer the coupling to a reservoir, and again, a lot of theoreticians have played a lot with reservoir couplings to generate a chosen Hamiltonian that you think is of interest. Okay, so let's look at the ion trap Hamiltonian again. Okay, so let's take a harmonic potential, and those ion traps that David was showing you, down the bottom of the well, they are pretty harmonic. They'll deviate from harmonicity further out as they become more excited, but at the bottom of the well, they're pretty harmonic. So I'll take a harmonic oscillator potential, I'll drop a two-level atom into it, and I'll drive it with a classical laser field, an external field that's coming in, so the coupling between atom and field is that Rabi frequency I'm making. And so it's a classical field, e to the I kx and e to the minus I kx, there's a phase phi. Okay. Right, so that's your basic Hamiltonian, and then what we'll do is start looking at where we can start to expand things out. So if we start thinking about creating and destroying phonons in the system, because you've got this harmonic oscillator, quantized energy levels, so by choosing the right sort of conditions, what you can do is to crank up these things. So basically, if I write e to the I kx in a harmonic oscillator, x I can write as a superposition of annihilation and creation operators, because it's a harmonic oscillator. Okay, so e to the I kx is just that now. E to the I, a number eta, and a plus a. That's just e to the I kx, where I've quantized x in the harmonic oscillator. So eta is this stuff over here. Okay? And what it really is just the Landicki parameter. It tells you the k vector times basically the wave packet size, done in this cold potential. So the Landicki parameter is just the wave vector times the size of the wave packet of the ground state in that potential. Okay, so there's your Hamiltonian. All I've done is say, let's quantize x, because it's a harmonic oscillator. But if this parameter is pretty small, I can expand that, because eta is going to be quite small. Okay, what we're doing is comparing the size of the ground state wave packet extent with an optical wavelength, after all. Okay, Raman it's different. I'm only talking about direct excitation. Okay, so if I expand it, what I can do is expand e to the I k dot r like that. If I get the first term, just eta, it's linear in AZ angles. That means my Hamiltonian has got 3 bits to it. There's the 1 bit there, and there's a bit over here, and a bit over here. These are the sidebands. So you have a carrier excitation, you have a red sideband, and a blue sideband. If you look at the red sideband, by choosing a small detuning equal to the vibrational frequency, what you can do is start driving essentially the James-Cummings model, except that now the field has been replaced by the vibrational excitations in the trap. Okay? So you create and annihilate phonons of excitation in the trap. That's the James-Cummings model. So what the hell is that? Well, if I go to this detuning over here, I get an anti-James-Cummings model. Okay? Where I create an excitation in the vibration by exciting the atom. Okay? That doesn't exist in any significant way of any importance in quantum optics, if you're talking about fields. But for ions, you've got this ability to use this detuning, and therefore you can drive it. Now that's kind of interesting, because if I chose that detuning, I can make a Hamiltonian, which nature really normally doesn't like the look of. Okay? So you can simulate a Hamiltonian that's sort of irrelevant but interesting. Okay. Right. So, heard about this from David. I can skip through this real fast. You have this array of qubits. Sirach and Zoller in their Fizzer of Leather shows you how to actually do this. And currently 14 bits is the record for these things. There's a whole raft of gate proposals over there. And they all work in one form or another, and they're hard work. Okay, these guys are doing heroic experiments. Okay. So if it is heroic and trying to scale this up, what can you do if you have a few qubits? As I've shown you, we can engineer a chosen Hamiltonian for that trapped ion. I showed you we could get a James-Cummings or an anti-James Cummings Hamiltonian. So can I do something about Bose-Hubbard, for example, or something else? Right. So why is it useful? To some extent, you built an analog computer because what you can do is tune your resonances. Nature gives you a fixed set of parameters, but what we can do is vary. We can vary the coupling constants by changing detunings, changing Ramsey frequencies. And whereas nature gives you one condensed matter system, we can make many. Not all chosen by nature. Okay. Right. So is it feasible? Well, you could build this MOT state in an optical lattice. You can do multiple spin species. And there's something funny here which, well, puzzles me at least, and some of you may know the answer. There's basically a threshold. If you want to get any sort of non-trivial computation done in quantum computing, you actually need a reasonable fidelity to do this, and that's why David, for example, was stressing the fidelity of their operations. But in some of the simulation work, it doesn't seem to require the same sort of fidelity. Right? I always find that a bit surprising. Okay. So optical lattices done large amounts of things. Okay. So let's look at a particular simulation. And that's a simulation of the Dickey model. So that's Robert Dickey. Dickey in the very early days of quantum optics came up with this idea of collective superradiance. Okay, many atoms acting like a huge dipole, and it will fire up as a sort of end-fire mode. There was a lot of confusion at the beginning as to whether what that was the laser. It's not. It's coherent collective spontaneous emission. Okay, and I actually wrote my thesis on this stuff. And then in the 1980s, especially Serge Roche's group working with Rydberg atoms showed how you could demonstrate these things. In the 1970s, mathematical theorists came up with a quantum phase transition, which I shall explain in a moment. Okay, it started with Hepp and Lieb. Q in Rochester did a lot of work on this. Reza Nardushi did a lot, and Moshe Nussensbach's book, Introduction to Quantum Optics, has a very nice illustration of it. But it's actually quite controversial, as I said. It's been revived. The cold atom people have looked at it again, and Esslinger and his group have looked experimentally at this in the most beautiful experiment. Okay. Right. So let's look at the thermodynamics of the Dickey model. Okay, it's like a James Cummings model, except that what couples to the field mode is not a single spin, but a collective spin. Okay, so more accurately, it's a Taylor's Cummings model. So it's field mode, lots of spins, all lined up together, and then a collective acceleration, a super spin with the field mode. Again, in this rotating wave approximation. And if you look at the energy as a function of that coupling constant, that's like a Rabi frequency over there, like the James Cummings Rabi frequency. As you crank up the coupling constant, you go from the normal ground state, where they're all in their spin down state, and there's no photons in the cavity, to a superradiant state, where some of the atoms are excited, and the field mode is excited as well. And that's the ground state. So there's a quantum phase transition at that point. Okay? So that's the Hepp-Lieb phase transition. Right. So that was what was observed experimentally by Esslinger's group in this paper published in Nature. And what they did, it's actually a beautiful experiment, based on some earlier theoretical work that Helmut Rich and others did, and some experiments that Vuletic did. Okay, and what we're really looking at is breaking some symmetries in this, as I'll show you. Okay, this is a very busy slide. So what you have is cavity, there and there, cavity. Okay, so what we're going to do is take a field mode, externally apply a field. So there's a cavity field there, okay, purely quantum cavity field, and a driving field that could be a standing wave, okay, because it's reflecting off that mirror. Okay, we'll have a detector over here as well, looking at the excitation of the cavity mode. And what we'll do is we'll look at the way the long-range ordering builds up in this cavity as a function of the Rabi frequency of this. And what's going to happen is that there'll be a scattering of the driving field from here via the atoms to populate the cavity field. There'll be a crosstalk, because what we're going to do is drive around the transition. Okay, so you've got this Hamiltonian, which is basically very much the Hamiltonian which you can engineer. It looks just like that Taylor-Cummings Hamiltonian. It's got various things in it, and it relates quite strongly to a paper that Tony Leggett wrote in 1970-71. Can a solid be superfluid? It's a very obscure paper, but it is what they were seeing. Okay, right. What happens in this is the scattering of the external drive standing wave field into the cavity field generates basically a two-dimensional optical lattice, where you can get cold atoms sitting in the right sort of position. Okay. But what you actually do is you build up this checkerboard pattern. Now, when you build a MOT transition, normally, what happens is that you start with a Bose condensate with long-range order. And as it condenses into the MOT transition, that's actually a Fox state with no long-range order. Okay, so you've got this funny symmetry breaking. What will happen in these is that there will still be a funny sort of order in this, and you build up a checkerboard where you'll either populate the even or the odd positions. It's like a checkerboard. Okay? Right, so let's look at the dynamics of this thing. Okay? You've got this Hamiltonian, you've got a standing wave in the x direction, okay? And what we're able to do, so there's my Z imposed external field, and there's my field that's varying because they're scattering between the external field and the cavity field. And what we're doing is we're driving a Raman transition, just like the things that David was showing you. Okay, so you've got lots of various sorts of Raman couplings in here. The scattering rate in getting from the external field to the cavity field, depending on the tuning down there, coupling constant, the pump amplitude. So that's the coupling constant to populate the cavity field. That's the coupling constant to drive from the external pump field. There's an order parameter here, capital theta, which is the expectation value of cosine kx, cosine kz. That's what I'm going to define as my order parameter. Okay? If theta is greater than 0, you get an even checkerboard, only the even size populated. If theta is less than 0, you get an odd checkerboard. In other words, you've got this parity thing going on here. Right, so there's my dynamical lattice potential. Okay, I can drive it away. And what I'm interested in doing is looking at the spatial ordering of forms inside this cavity. We want to see how they're populated, and we want to see how the field populates. So the field damping is relatively small in this. Okay, so you can do some adiabatic elimination. You basically got a kind of MOT geometry, but spontaneous symmetry breaking here is this relative phase between the pump and the cavity field. And so, whereas the MOT lattice has no long-range order, this will have long-range order, which is kind of odd and interesting. Okay. So what do they see? Right, so you start with initial Bose condensate. So in the x direction and the z direction, we're going to assume you're based on the ground state. Okay? You take that Bose condensate and you crank up your pump field. The pump field then scatters into the cavity field. And so what happens in that scattering is you make momentum components plus or minus hk. Okay, both in the x and in the z direction. Okay. So you get this coupling between 0, 0. I don't know what happens to the end of that state vector. Should be, somehow it's got eliminated. So you get this collective coupling to and fro, and basically it's the Dickey excitation, like so. So experimentally what they see, I'm not sure how well you can see this, you see this ordering as you crank up the driving field, and you get this critical phase transition where the field suddenly turns on, blip. So we're in the ground state, and now the field is suddenly turned on. And the atomic distribution has suddenly gone out into the checkerboard with this even and odd. So, there you go, works. A beautiful example of an observation of a Dickey phase transition, very odd sort of quantum state. problem is, there is no such thing as a Dicke phase transition. It doesn't exist. And the reason it doesn't exist is that it's fairly straightforward to show that if you have a gauge invariant Hamiltonian that's coupled together between light and matter by fields that respect what's called the Thomas-Ricci-Kuhn sum rule, which is basically unitary dynamics, the TRK sum rule, there is no quantum phase transition of the Dicke type. So Bieniczky, Beruna and Zharzewski, or it's the no-go theorem, there it is, saying this don't exist. And the Essinger experiment is beautiful and saw it. Isn't that a puzzle? So what did they see? What they could demonstrate is a Hamiltonian that nature abhors. In fact, doesn't even allow. But by changing coupling constants, by changing detunings, you can generate a dominant terminal Hamiltonian which nature won't allow. But you can make by simulation. Just as in the ion trap, I can make an anti-James Cummings model. So this simulation saw a non-existent quantum phase transition. It's really beautiful. There's nothing wrong with the experiment. What they saw, you know, I've only shown you the statics. All sorts of folks have been playing around with the dynamics of this, but it is not a demonstration of what happens in nature, because in nature, in the gauge invariant Hamiltonian, it don't work. So, right. There may be a way out. For example, in circuit QED, maybe you don't have to obey the DRK sum rule. So there's a paper in Nature Comms we don't really understand, which is looking at that. What are we doing for time? I think I might skip the safe codes. You know all about crypto anyway, don't you? Of course you do. Yeah, it works. Okay. In my view, the one that really is provably secure is anything that involves violation of Bell's inequality, which is actually what Arthur Eckert showed at the end of his PhD thesis with me, when the Eckert protocol was derived, because basically it depends on the monogamy of entanglement. You can't, you have a monogamous version of this, so an interceptor can't actually share that and still have Bell violations. You have to be careful, like in any crypto system. I've skipped all that stuff, but you know, operator errors always allow you to creep into an encryption system, and there are all sorts of interesting blinding attacks that you can do. And there are ways of getting around them as well. Okay, I promised to show you why washing makes you heavier. Okay, so now we're going to shift to quantum metrology. So some quotes on metrology. Okay? Right. There's a nice one. The Lord abominates a false balance, but a just weight is it. That's the earliest one I could find in metrology, from Proverbs. Whitworth, he of the screw, you can only make as well as you can measure. But this is my favourite. This is from James Clerk Maxwell. And what Maxwell said is that if you want standards of length, time and mass, which are absolutely permanent, then you don't do it in terms of artifacts. You link it back to something which is basically imperishable. He said basically atoms. We actually use the word molecule there, doesn't matter. Okay? So in 1870, Maxwell was already proposing a unit system which depended upon basically quantum objects. And he was absolutely right. Okay? And all of our unit systems do actually depend only on atomic things, except for one, and that's the kilogram. Okay? There is no quantum mass unit as yet. Okay? So seconds, length, all the rest of these things, all the SI units, except the kilogram, are now determined by atomic standards. Atomic clocks make GPS happen, they've got all these accuracies. The kilogram is the last to depend on an artifact. The standard yard was a lump of wood that was kept in the House of Commons for security. In the middle of the 19th century, the House of Commons burned down. Fortunately, the Royal Society had a copy. So you mustn't depend on artifacts. So the kilogram depends on a lump of stuff inside a bell jar, inside a safe, in Sèvres, in France. And then there are 9 copies, and those 9 copies are shared out amongst the standard NMO labs around the world, and all mass units are then compared with that. And every now and again, what happens is they have to take this out of the bell jar and wash it. The act of washing, we know, removes about 50 micrograms of material. But that lump of stuff's defined as a kilogram. It can't get lighter because that's a kilogram. So the act of washing has made everything else in the universe heavier. Okay? Now that is really repugnant. Okay? It just demonstrates the fallacy of depending on an artifact. So a lot of work has been done to try to do something about the kilogram. Okay. So there's the standard unit. We actually, within research, there's 2 separate ways of getting atomic standards for mass. One is the using Avogadro's number and the silicon sphere, and that's looking reasonable. The other method is a thing called the Watt balance. The Watt balance was invented by Brian Petley at the National Physical Laboratory, and what it is a null experiment where you basically set a mass vibrating, and then you basically stop it. And you stop it by an applied electromagnetic field, and you read the current and voltage from Josephson and von Klitzing, and then you can work out the mass from those. They're atomic standards. That's the Watt balance, and it's looking quite promising. Okay. So it could well be, within 5 years, we may well have a system of determining mass which doesn't depend on everything else in the universe getting washed, getting heavier because you washed it. Right, I'm going to close, and I want to do one more thing. That's the Casimir force. Does anybody not know what the Casimir force is? Brilliant. Okay. I'll explain. Right, there's Casimir, roughly sort of slide. Actually doing reasonably well. First ever 4th order QED calculation was done by Casimir, working in Phillips, to explain the stability of life over colloids like paint. But what he came up with at the same time is that if you have a cavity, empty cavity, and you look at the space in between the cavity mirrors, there's 0-point energy, but of course you can't support those long wavelength modes if they don't fit in the cavity. Okay? So what you basically get is a force between these 2 plates. The force depends on the distance between the plates, so d to the minus 4. So there's a d to the minus 4, there's a lot of numbers over there, and that's a purely quantum mechanical thing. Okay? Lots of people have been looking at these things. Okay? So that's the Casimir force. Okay? And you measure torsion balances and so on. Steve Lamoureux has done a beautiful experiment with these, others have been looking at these things. AFMs have helped in some of these determinations. Okay, so there's the prediction. So there's 1 over d to the 4th, Planck's constant, speed of light, nothing else, just geometry. Okay. First measured actually by Kitchener and Prosser. I'd love to say in the physics department at Imperial, but it wasn't. It was actually in the mechanical engineering department, and these guys were tribologists, wear and tear guys. Okay? And there's the 1 over d to the 4th law of the speed vibration. Okay, why is that interesting? Well, if you do imaging at the atomic scale of the kind that Martin talked about, one way of doing it is an atomic force microscope. You have an oscillating tip, you've got a little atom at the end of it, you can measure the force between the oscillating tip and a sample atom and a lattice. And so you can move an atom, say that cobalt atom, from one lattice spacing to another place, and it takes about a piconewton to move a cobalt atom 160 picometers. Okay? So AFMs have got all of these sorts of things. The problem is how to calibrate an AFM. If because without calibration, what you're doing is basically geography. You know, you've got pictures of stuff, but you don't know the relative numbers of them and things like this. And so it's interesting to see how you might want to calibrate some of these kinds of things. And that's why we've been doing some playing around about this, because just as the kilogram has a lot of stuff, and you do a null measurement, and measure by the electrical force that stops the gravitational attraction, and you read out from von Klitzing and Josephson, here you can do the same with an AFM. And that idea actually came from Peter Clemson, who's now in Newcastle, to actually take a nano cantilever, and I saw there were a number of those kinds of things in the posters. If you take a nano cantilever, what you're basically seeing is that piconewton sort of thing that we just showed you to move a cobalt atom is the same size as the Casimir force. But the Casimir force only depends on Planck's constant, the speed of light, the separation, and some geometry. Okay? So you've got a fundamental SI unit of atomic force. If you could do a Watt balance with an AFM cantilever and calibrate it against Casimir. So there's quite a lot of effort being done to try and link up the atomic force microscope forces with Casimir forces at the same distance, because the same sort of distances for Casimir force, same sort of size forces, so it's quite likely that you could build exactly that. Right, so why do you need accurate measurements? You should rely on it. There's the obvious reason, so you get reproducible, reliable scientific measurements. You need to maintain international trade. When you send stuff around the world, you better understand the dimensions or the quantity of stuff is what you say it is. So we did some estimations of what it costs the UK economy to do precision measurement, just the UK economy. This was a thing I did for what was then the Department of Trade and Industry and is now BIS. It's amazing. Measurements in the UK cost £50 billion. Okay, the total annual science budget, research science budget in the UK is just over £4 billion. Okay, so a little bit of improvement in these measurement systems that I talked about can address this on here. This is something I keep driving home, especially to ministers, especially chancellors of the exchequer. Right. This is just a precursor. What's the biggest quantum business in the world? It's that. Okay? That's satellite imaging put together for the greening of the world season by season. Okay? It's photosynthesis. You can see it from space. Right? The trapping of photons by molecular trap sites in early stage photosynthesis is the biggest business in the world. The only reason we're here. Okay? And there's lots of evidence that there's some early stage quantum coherence in this. And can you engineer it to be better? Because this is big stuff. You can change that. And at that, I'm going to stop, I think. Yeah. Right. Lots of stuff heading to market. This is from Franco Nori's article in Physics World. I shouldn't have done that, should I? Got away with it. You know, which things are actually coming out to be quite useful. Does anybody know how D-wave works? Anybody know what D-wave is? Okay, so there is a market, but I still don't understand how it works. Okay. But, you know, lots of stuff close to market, okay? So what I've tried to show you is that we've benefited enormously from quantum effects and quantum technologies. Some of them are blindingly obvious, like the urban doped fiber amplifier, like transistors, MRI, and all the rest of it. We are wholly dependent on GPS. GPS is wholly dependent on atomic clocks. I've shown you where you can do a lot more on this. There's lots more to exploit, and what I've shown you with this little tiny hint of how nature may be exploiting it is really a precursor to what I think Martin's going to tell you a bit more about tomorrow. Thank you for listening.